Welcome to Easy Elim Learning Simplified. My name is Ruth, and today our topic will be properties and trends across a period. So, today you're going to be looking at the physical properties of period 3 elements. This is going to be a consecutive lessons in regards to this topic. This topic is usually tackled under chemical families and part of it under body. So, what we are going to do is merge these two subtopics, or like you match the different topics together and put them in one. So you look at the properties of period 3 and also the type of bonds in the oxides and fluorides in period 3 in the coming videos. So for today, we look at the period 3 elements, what are they and where are they at in the periodic table, and then you look at some of the physical properties and the bonds also in those elements, and then you tackle like a few questions. So a period is a vertical row of elements in the periodic table. We discussed this. Elements in the same period have the same number of energy levels. And there are usually 7 periods in the periodic table except for the lanthanides and actinides, which are not assigned specific periods. And then period 1 to 3 has few elements because they lack the D block elements and have only S block elements and the P block elements. So there is a SPDF orbitals that explains how we usually write the configuration that is beyond like what we do in high school. So we talked about the 2888 configuration, but it's actually usually arrange this number of electrons in their different orbitals, and we have the SPDF orbitals. So we're not going to discuss that, of course, in this level, but it's something that you can like research more about. Then, so the S block is usually for group 1, group 2, D block for transitional elements, P block for group 3 to group 8. So when you look at the periods, you can see the periods. We have period 1 with hydrogen and helium, period 2 with lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. And then period 3, which is going to be our main focus for this lesson, which is consists of sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and argon. We have other periods, and of course we talked about the lanthanides and actinides, which are not like given a specific period. So the period 3 elements usually have 3 energy levels, and they consist of 8 elements from sodium to argon. It's only made of S block and P block elements and lacks D block elements. So we have sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and argon. And we say that they have 3 energy levels. So we'll look at the configuration later on when we are discussing some of the properties. So some of the physical properties of element 3 is electrical conductivity. You'll notice when we are discussing these properties, they may not have like a gradual increase or decrease across the period. Some of them might, but remember they have been divided into two. You can see when you go back to the previous slide, you can notice that sodium, aluminium, and magnesium are metals. Phosphorus, sulfur, chlorine are nonmetals, and argon and silicon is a semi-metal. So you notice some of the properties may not gradually increase or decrease. Some may, some may not. So you notice you'll be dividing them. We'll be tackling sodium, magnesium, and aluminium together, and phosphorus, sulfur, chlorine together in most cases. So one of the properties we talked about is electrical conductivity. So sodium, magnesium, and aluminium are good conductors of electricity. They are good conductors of electricity first because they have delocalized electrons in their structure. This is what conducts electricity. But the conductivity increases from sodium to aluminium. We discussed this in metallic bonding. The reason why conductivity increases from sodium to aluminium is because there is an increase in delocalized selection. So aluminium has the highest number of delocalized selections, which are 3. Then sodium has 1 delocalized electron. Magnesium has 2 delocalized electrons. So you notice, yes, they can conduct electricity, but aluminium is the best amongst the 3. So I said when you ask this question, be specific on the number of delocalized electrons. In the metals, the electrical conductivity decreases with increase in temperature. So when the temperature increases, conductivity reduces. The reason why this happens is because temperature usually distorts the alignment of electrons, so it prevents an easy flow of like electrons or electricity, which causes poor conductivity. Phosphorus, silicon, and chlorine and argon do not conduct electricity. We have molecular structures. You can see how we are grouping them together, and all the electrons in the atoms are used in bonding. These are nonmetals, so you notice if they are molecular structures, it means they have covalent, but they share electrons. So they do not have any delocalized electrons. That's the reason why they do not conduct any electricity. As for the silicon we call it a semi-metal. It conducts electricity, but in special conditions. For example, if you increase the temperature of silicon, it actually conducts electricity more. Unlike the way we were talking about increasing the temperature of the metals and the conductivity goes down, for silicon, if you increase the temperature, the conductivity goes high. It is a semiconductor, making it very unique among this period. So a semiconductor is a crystalline material which conducts electricity under certain conditions. Another property is the atomic radius and the ionic radius. So this is a very common question. The atomic radius of period 3 usually decreases across the period. So the reason why it decreases across the period is even though we have the same number of energy levels, the number of protons are increasing gradually across the period. This leads to the increase in the nuclear charge while the shielding effect remains the same, hence decrease in the atomic radius across the period. So let me clarify what we have just said. So when you look across the period, let's take for example sodium, magnesium, and aluminium. So the configuration for sodium is 2.8.1, for magnesium is 2.8.2, aluminum is 2.8.3, and so forth. Silicon is 2.8.4. So what you notice, the number of energy levels are remaining the same across. But what is increasing, first of all, is the number of electrons in the outermost shell. So the electrons that are being added in the outermost shell, we say they do not have any effect. The effect is negligible. They don't have any effect because the number of energy shells inside remains the same. They are being protected or shielded by two energy levels. You can see the one with 2 and the one with 8. 2, 8, 2, 8, 2, 8 is the same across. So for them, even if we are adding an extra electron, it's not really going to affect anything much across the period. But the biggest effect happens in the proton. Sodium has 11 protons, magnesium has 12 protons, aluminium has 13 protons, silicon has 14 protons. The protons has a bigger effect, that extra proton across, than the number of electrons being added. So because the number of protons are increasing across the period, there is an increase in nuclear charge across the period. And the moment the nuclear charge increases, it means that like the outermost electrons are going to be pulled very strongly to the nucleus. That is the reason why you can see even from the image the atomic sizes is decreasing across the period. So this is one of those properties that is gradually across the period, and you can see why. So that is also the same reason we talk about atomic radius. Atomic radius, ionic radius is when these electrons have in the case of the metals, they have lost electrons. In the case of the nonmetals, they have gained electrons. So when you look at the ionic radius as well as you grow across the period, they also decrease. So the melting point and boiling point. So sodium, again, you pick them three together because they are metals. Sodium, magnesium, and aluminium have very high melting points because they have giant metallic structures with strong metallic bonds. You've had this question, you have been told using structure and body, explain why sodium and magnesium and aluminum have very high melting point. So you see how the statement is coming in. They have giant metallic structure. You mentioned the structure and you mentioned the board. Because the board needs energy to be broken, that's the reason why there's an increase in the melting points. So the melting point and boiling point usually increase from sodium to aluminium, and we say the reason why this is so is because of the increase in the delocalized electrons. We discussed this in the topic metallic bonding. You can go back and check it out. Also, as you move across the period, also the size of the atom decreases. We said also size affects the strength of the metallic bond. And you notice between sodium, magnesium, and aluminium has the smallest size because it has the highest number of protons, which means it has the highest number of nuclear charge. So that's the reason why it has very strong metallic bonds. If you look at its melting point and boiling point, it's so high in comparison to sodium and magnesium. So silicon, so we move from after we discuss the three metals, we go to the others. Silicon is an nonmetal, but it has very high melting points and boiling points, so high actually, even in comparison to the metals, because it has strong covalent bonds. It is a giant atomic structure. So it needs a lot of energy to break. For the phosphorus, sulfur, and chlorine and argon, they have very low melting points. This is because they have molecular structures, and since they are molecular, it means they are bonded, their molecules are bonded with weak van der Waals forces. You notice we have weak van der Waals forces in phosphorus, in sulfur, and chlorine, and then for the argon, it's between the atoms. So when you look at the atoms, argon atoms, in between those atoms, because they are monoatomic, in between the atoms you have the molecular structures. But for phosphorus, sulfur, and chlorine, it's between the molecule. And then the melting point usually decrease from phosphorus to argon, as you have said. As you go across a period from phosphorus to argon, the size of the atom also decreases, leading to smaller atoms and hence molecules. So remember we talked about the size of the van der Waals forces being affected by the size of the atom. So the bigger the molecule, the stronger the atom. And when you look at the phosphorus exists in different atoms. You have P4, S is going to be S8, Cl2, and then argon is going to be 1. So you notice that we also have P5 as well. As the size of the molecule decreases across a period, so does the van der Waals forces, their strength decrease. So that is the reason why the melting point is decreasing across the period. Phosphorus and sulfur usually exist as solids at room temperature. This is because of their strength in the van der Waals forces is very high in comparison to chlorine and argon. So they have giant molecular structures while chlorine and argon have simple molecular structures. So this is just a summary of what we have discussed. You can see sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. And the thing that you need to pay a lot of attention in is the structure and board, which affects a lot of properties here and also the sizes. So sodium is giant metallic, magnesium giant metallic, aluminum giant metallic, silicon is giant atomic, it's covalent, and you see it forms some of the highest melting point. You can see how it's so high. And then phosphorus is molecular, sulfur is molecular also, chlorine is simple molecular, and also argon is simple molecular. So these ones have van der Waals forces between their molecules. So let's do a few questions. Explain why there is a general increase in the fast ionization energies of elements in period 3 of the periodic table from left to right. So when we talk about ionization energy, we are talking about the energy required to lose an electron. We said that across the period, the size of the atom is decreasing. Across the period, it's becoming smaller and smaller and smaller. So you will notice that when you move across a period, because there is an increase in the number of protons, which increases the nuclear charge. If the nuclear charge is increased, it means the outermost electrons are held closely to the nucleus. So it will require more energy to remove any outermost electrons in the outermost shell. So you can imagine across the period it's becoming stronger and stronger or harder and harder to remove electrons from the outermost energy level. That is the reason why the ionization energy increases from right to left. Protons, increase in nuclear charge across the period, more energy being required to remove the outermost electrons. And then element Q, S, T, U, R, and P belong to the same period in the periodic table, and the ions formed by the atoms of the elements are given below. So you have Q, U, T, R, P, and S. Arrange the elements in order of their increasing atomic size. So when we talk about increasing atomic size, we said that first of all, it decreases from sodium to argon, but it doesn't mean it's specifically that, but you'll see if it is or not. So the ones that are losing electrons, or the positive or the metons, are the ones that have bigger sizes, and the nonmetals have smaller sizes. And the more electrons that is being gained, the bigger the size. So this is what I'm meaning. So let's arrange it normally as it would be across a period. So we would start with the one that is losing one electron. Let's look for that. So P is only losing one electron. We go to the one that is losing two electrons, which is Q. So we are in magnesium. And then we have the one that is losing three electron, R, 3 plus. And then we go to the one that doesn't lose again, the one that is 4, we don't have it. So we go to the one that is going to gain 3 electrons. So we go to S3 minus. And then we go to the one that is going to gain 2 electrons, sulfur. So it becomes T2 minus, and then chlorine, which is going to gain 1. So this is normally how it is, and the sizes is decreasing in this manner. So if you want to put the answer the way we have been asked, is arrange the elements in order of the increasing. It's supposed to be the other way around. So our answer is going to be U minus, then T2 minus, then it's the elements, not the ions. So it's going to be U, then T, then S, then R, Q, and P. So it's going to increase in this manner. And then finally, explain why aluminium is a better conductor of electricity than magnesium. So we said aluminium has more delocalized electrons. So it has 3 delocalized electrons, which conducts electricity better than magnesium, which has 2 delocalized electrons. So you be specific when you're doing your explanation. So that brings us to the end of this subtopic. So next, we are still going to continue with period 3. So we are going to go to the chemical properties of the period 3 element. See you then.